Yes, today we are discussing the ion formed by oxygen by removal of its one electron, of course, from outermost energy levels. Two approaches are there. One, we can consider complete molecular orbital diagram for oxygen molecule, and from that molecular orbital diagram, from those molecular orbitals, I will remove the electron. And other way, during formation of oxygen ion only, I will consider different species. Means if O2 plus I have to explain, then I will consider oxygen atom at one side, means its orbitals, I can say atomic orbitals, and O plus, that's a ion, oxygen ion, positive ion, and its orbitals. Combination of those orbitals following LCAO method, I'll get various molecular orbitals, and in those molecular orbitals I'll distribute the electrons. Here energetics of various atomic or ionic orbitals should be clear to you. Therefore, I am discussing this approach of explanation of formation of molecular ion O2 plus.
Pay attention towards three compartments. Left compartment is atomic orbitals of oxygen. Right compartment orbitals of O plus. And middle compartment molecular orbitals of O2 plus. About oxygen concept is very clear, 2s then 2p orbitals. My point of emphasis here is the energy levels for orbitals of O plus. Just compare O and O plus. How can we obtain O plus? By removal of electron from oxygen. Means electron from one of the 2p orbital is removed. So now in O plus, how many electrons are there? 7. And how many protons are there? 8. And what was the situation in case of O? 8 protons were there and 8 electrons. So number of proton, number of electrons were same in the O atom. But here number of electrons are less. So relatively nuclear charge, nuclear force in O plus increases. O plus will shrink. O plus will contract, its size will decrease. Size decreases means orbitals comes near to the nucleus. Therefore, I have represented there 2s orbital of O plus is of low energy than 2s orbital of oxygen. Similarly, 2p orbitals of O plus are of lower energy than 2p orbitals of oxygen. I want to give you the clear-cut insight about the molecular orbital diagram. Therefore, these energetics and form molecular orbitals are represented. As usual, three conditions of LCAO. First condition, combining atomic orbitals should be of same. But here same word will not be applicable. What is the other option there? Or similar. Yes. Energy of 2s orbital of oxygen and 2s orbital of O plus are similar. Similarly, 2p orbitals of oxygen and 2p orbitals of O plus will be of similar energy. So first condition is fulfilled by those orbitals which have shown are combining. Second condition, they should be of same symmetry. Yes, there is no compromise for this condition. 2s orbital of O you consider or O plus you consider. Symmetry is same. Which kind of symmetry they do have? Sigma symmetry. What about 2p? There are cluster of 2p orbitals. 2px, 2py, 2pz. Conventionally, I am considering 2pz orbital is bonding orbital. 2pz orbitals are along internuclear axis, bonding axis. So 2px and 2py will be perpendicular to it. Who can form the axial overlap? Who can form the strong overlap? Who can form the strong interaction? 2pz orbital. What is the symmetry of 2pz? sigma because it is along internuclear axis, and if we rotate that 2pz orbital along internuclear axis, z axis, lobes will remain to their proper position. Positive lobe will remain to positive side, negative lobe will remain negative side, and I have represented by yellow coloration 2pz orbital. So sigma symmetric 2pz orbitals will combine to form bonding 2pz orbital sigma 2pz and anti-bonding 2pz orbital sigma star 2pz. The energy by which bonding orbital decreases, that much amount of energy anti-bonding orbital will increase. Stability and instability are nearly equal. It is from general chemistry point of view to understand the approach, LCAO approach. And remaining pi symmetric orbitals, visually 2px and 2px, 2py and 2py, they will combine to produce pi symmetric bonding orbital pi 2px and pi 2py, which are of same energy level, and pi symmetric antibonding orbitals pi star 2px and pi star 2py, which are higher in energy. The decrease in energy of pi 2px and pi 2py relative to average energy of 2p orbitals of oxygen O plus is equal to increase in energy of pi star 2px and pi star 2py. I repeat, here while considering decrease in energy for molecular orbital or increase in energy for molecular orbital with respect to what? With respect to combining orbitals. So how to find the actual energy level of combining orbitals? Average energy. Average line we should consider, imagine, and from that line decrease and increase can be measured. Stability or instability can be understood. By green coloration, I have represented here pi symmetric 2px and 2py orbitals, and respective molecular orbitals generated also are represented by green coloration. Extent of interaction by sigma orbitals is more. Stability of produced bonding orbital is more, is lowest in energy, and instability of antibonding molecular orbital produced by sigma interaction is also more, so highest in energy. And pi orbital interaction, lateral interaction, relatively weak interaction, stability governed by respective orbitals will be lesser than the sigma interaction. Similarly, instability governed by the antibonding pi orbitals will be lesser than the instability of sigma star to pz. Now once these energy levels are clear, let us distribute the electrons. Here I had not represented the 1s orbitals from oxygen and from O plus, that's a cation of oxygen. Why? Because 1s orbitals are inner. As per third essential condition of the LCAO principle, inner orbitals, they do not undergo appreciable proper overlap, therefore they will remain non-bonding. Previously what was happening till now, all 1s orbitals were of same energy, but here 1s orbital of oxygen will be of higher in energy than 1s orbital of O plus. So energy sequence will little change. 1s orbital of oxygen or oxygen ion has two electrons. How we represent that? 1s means is the first shell. First shell means representation is K. So K is a representation for 1s orbital of 1 oxygen. Similarly, K is a representation for 1s orbital of O plus. What do you think? Whose energy will be lower? K of O plus or K of O? Yes, K of O plus will be of low energy because O plus has positive charge, effective nuclear charge is more, and because of that 1s orbital will come closer. As it comes closer, energy will be lower. Therefore, while representing electronic configuration, K comma K separately I need to represent them. No doubt, for total 4 electrons will be there, but K electron 2 and other K 2 electrons in the non-bonding orbitals. What about the bonding orbitals? Sigma 2s, then sigma star 2s, then sigma 2pz, then pi 2px, pi 2py are degenerate, pi star 2px, pi star 2py are degenerate, and sigma star 2pz is highest energy level as usual. In this following Boole principle, Hund's law of maximum multiplicity and Pauli's exclusion principle, we have to distribute the electrons. So 4 electrons already we distributed. What is the atomic number of oxygen? 8. O2 means 16. O2 plus means 15 electrons we have to distribute. Out of that 4 electrons already went in non-bonding orbitals KK. Next 2 electrons will enter in sigma 2s. Next 2 electrons in sigma star 2s. Next 2 electrons in sigma 2pz. Next, that's which electron? 11th electron will enter in pi to px, 12th electron in pi to py, 13th electron in pi to px, 14th electron in pi to py, and 15th electron has no alternative, will go to the higher energy level and electron will enter in pi star to px, say one of the antibonding pi orbital. This is the electron distribution. From this electron distribution, can you find bond order? Bond order is equal to number of electrons in bonding orbitals minus number of electrons in antibonding orbitals divided by 2. How many electrons are there in bonding orbitals? 8. How? 6 electrons in bonding orbitals caused by 2p set and 2 electrons in 2s. How many electrons are there in antibonding orbitals? 3. How? 2 electrons in sigma star 2s and 1 electron in pi star 2px. So 8 minus 3 divided by 2, answer is 2.5. So relative to O2, O2 plus is strongly held. O2 plus is strongly binded. How many unpaired electrons are there? 1. And because of that 1 unpaired electron, the O2 plus will be paramagnetic in nature. Let us understand its electronic distribution. See there, non-bonding orbitals K and K means two shells are there. First K is what? It is a non-bonding shell by O plus. Second K is a non-bonding shell by O. Comma is represented in between, indicates to have different energy. And in first K, 2 electrons are represented. In second K also 2 electrons are represented. Both K shells are non-bonding. And our bonding orbitals starts from sigma 2s, which has 2 electrons, sigma star 2s 2 electrons, sigma to pz 2 electrons, pi to px and pi to py. Their energies are same, therefore is equal to sign is there. Each has 2 electrons. Pi star to px 1 electron, pi star to py energy is same compared to pi star to px, so is equal to sign is there, has no electron, and sigma star to pz has no electron. Here non-bonding orbitals are represented by green blue coloration and all molecular orbitals bonding anti-bonding are represented by white color. I represented electrons in bonding orbitals by white color and electrons in anti-bonding orbitals by yellow color. Now from this electronic configuration, you will find one unpaired electron pi star to px. Because of that it is paramagnetic in nature and it will be easy for you to find the number of electrons in bonding and anti-bonding orbitals with the help of color. Bond order will be 2.5. Yes, now you are understanding more about the molecular orbital theory. Yes, it is a very important theory. As a homework, you have to compare the two atomic orbitals. One atomic orbital, that's a 2s orbital of oxygen, and other 2s orbital of O plus. What do you think? Which orbital will be of low energy? Whether 2s orbital of O or 2s orbital of O plus? Write your answer in comment box. I am waiting for your answers.
From this explanation, the idea about the energetics of various ions might be clear to you. If charge changes, then how the atomic orbital's energy level changes. Accordingly, their contribution to molecular orbital changes. The concept will be more clear next year when you will study heteronuclear diatomic molecules. But at this moment, the energetics I wanted to make the clear shortly. Then removal of electron from anti-bonding orbital has increased the bond order by 0.5 and bond order for O2 plus became 2.5. That also you understood, and because of the presence of one electron it is paramagnetic in nature. Now we understood O2 plus. In next part let us discuss other ion of oxygen, that's O2 minus.